Okay, so welcome back student. So let me start with where I stopped in my last class, which is the Gram-Schmidt orthonormalization. So these are the formalism using which I can figure out a set of orthonormal bases by using a set of linearly independent vectors. So linearly independent vector is given. From using that I am going to find out a set of orthonormal bases. So if I look it in this way, so for example, this quantity, try to first figure out what is the meaning of this notation. So one notation I use this, what is the meaning of this notation? So normally we know how to calculate this, but this I do not know. So if I write these as this way, so y1, say, let me just write y to make it simple, because I need to use the component. So say y1 and y2 are the two components of the vector y. I need to calculate this notation. What is the meaning of this notation? First I need to find out. So then y, which is in this is a bra notation and this is a Kate notation. You are familiar with this notation. I need to write this in this way. So these things, whatever I am writing here, is coming from this dual space concept. So you know about this. Here, since y is a real vector, so I am not going to write this as a star. Normally in principle you should write it as star. So now this quantity in the vector notation, these and this can form something like this. So operation is this and this. So y1 square, y1 y2, y2 y1 and y2 square. If it is not y1 y y, if it is xy, for example, if it is something like this, the result will be x1 x2 in general, y1 y2 in general, then it will be x1 y1 x1 y2, this multiplied by this multiplied by this, here, this multiplied by this multiplied by this. So this forms a matrix, and this is called the outer product. There is a name. This is called the outer product. So that means inner product we are having a, from this I am having something, a scalar that we know. When I do the outer product of two vector by taking in this way, I am getting something which is matrix, 2 by 2 matrix, which behave like a operator. So this is something that is operating over something. So what is the meaning in there in this Gram-Schmidt orthonormalization process? What is the meaning of that? So let us try to find out. It is nothing but yi, this quantity is called the projection operator. Very important term, projection operator. If a vector is given along this direction, and if this is the direction of say yi, if I operate this quantity, which is now behave like a operator, if I operate this quantity over this vector, given vector x, it essentially means that I am taking the projection if I say this projection vector xp, say I write this as a new vector xp, which is the projection of this x vector xp. So, what will be my xp? Xp will be this quantity. And which is quite simple. If you try to understand that, then yi x, this quantity is nothing but the dot product or this quantity multiplied by the vector direction this. So, it will give you the vector along this direction. So, that means it is projection along this direction. So, in this case, try to find out how this projection operator works here, especially here in this particular case. So, this equation was y2 was something x2 minus y1 x2. This was my y2 prime. How to calculate the y2 prime? That is that. So, my x2 was in this direction. Say this is the direction of my y1. So, this vector is the x2 minus the projection. So, projection, I just say that this vector is this one. This is the xp, the projection vector that I do, and here what I am trying to do, I am just trying to find out that what is my x2 minus this. This is my x2 vector, and if I subtract from this vector, then essentially what I am getting is this vector. This vector is nothing but x2 minus xp, this vector, this perpendicular vector. So, now you can see that x2 vector is giving to you, x1 was also in this direction, because y2 is nothing but x1 mod of this quantity. So, it has to be this direction. So, now using these and this vector, I can figure out another vector which is perpendicular to y1. So, this is exactly perpendicular to y1, and which is x2 minus xp. Xp is nothing but this projection operator thing. So, that means I calculate this one, then subtract from this and this, I will get a new vector which is perpendicular to this. So, this is the concept. Every time if you able to do that, you will start getting a vector which is perpendicular to the previous one, and with this you can calculate the entire set of vectors which are orthogonal to each other. So, now let us find out more about this projection operator. So, if say E1, E2, En are set of n vectors which are linearly independent of each other as well as orthonormal. So, that means they are forming an orthonormal set, mathematically means this is satisfied, this thing is satisfied. If this is satisfied, if these things are satisfied, then any vector can be represented in this form, that is one issue. Second thing is that I need to find out this quantity. This is a projection operator along any direction I, any preferred direction. So, there will be different directions. So, 1, 2, 3 is corresponding to the different direction. So, I is a some direction, and now I try to find out this quantity. So, 1 to n. So, sum of all this quantity. So, sum of all this quantity is essentially the meaning of this is that I try to project all possible direction of a vector. So, what will be the value of these things? This will be an interesting thing. So, this is a projection operator along ith direction. Now, I try to find out the summation of all the projections. So, if this is a projection in I, if I run this I from 1 to n, so it essentially mean I try to find out this quantity ei plus e1 plus e2 plus en. What will be the summation of entire things? All the projection operator, if I sum, if they are orthonormal to each other, then what I am getting? So, let us try to find out. So, I need to find out this. So, what I will do, that I will take a vector x. This vector can be decomposed by this basis. So, e1, e2, en. So, this is the decomposition of this vector along the basis. Now, I need to use this over that. So, I will, what I will do, that I will project this projection operator, entire projection operator over x, big X, and try to find out what I am getting in the right hand side. So, essentially what I am doing these things. What is my x? X is x1 e1 plus this. So, this is the thing I want to operate over that and try to find out what I am getting. So, term by term, if I look, that what will be my first term, it will be I, and it operates over the first term. So, I and I, it will give 1. So, I will, first term will be this. All the second term will start at 2 and 2, and if I say this is 1, then it will operate over this and this and this. So, if it is 1, then it operates over this, and this 2 and 1 will cancel out, and 3 and 1 is cancelled out. So, all the other term will going to vanish. The second thing is that the next term, which is E2, which is E2. So, E2 when I operate over this first term, it will going to vanish, because E2 and E2 will going to merge and gives a 0 value. E2 over that we give 1, because this thing over this operation give you some non-zero value. So, my next term will be something like this. In the similar way, my third term, which will going to survive, is something like this up to n. So, what essentially, after operating this over that, what essentially I am getting my old vector, which is x. So, I operate a projection operator over x. As a result, I am getting my old vector x. So, if I write this here, then I should write it 1 to n ei that operates over vector x minus vector x is equal to 0. I take this x this side, and my equation is something like this. From here we can write a very important expression which is essential in quantum mechanics also. This 1 is basically a matrix, because just before I show that these things, this quantity gives you something which is matrix, is a matrix form. So, I should write it 1 because I am taking x common out of that. So, if I take x common out of that, as if this is 1 normally, but since this is a matrix operation, I need to write 1 in this way. You should understand that this is an unit matrix. So, now from here I will have a very important expression. This is a special name of that, this expression, that projection operator over entire all the direction. If I take it, essentially gives you the unit vector, the something unit matrix. So, this is called, this special property called completeness. This special thing called completeness. So, now I can check that in principle that whether this is giving you some kind of completeness things or not with my usual basis. So, that quickly to understand how this is working. So, let me do that for 2D, which is easier. E1 E2, I know that these two are orthonormal basis. If they are forming orthonormal basis, readily they will follow this rule. Sorry, here I am writing a wrong expression somewhere. It should be something like this. Orthonormal this. By mistake I write the projection operator notation. Please note that. If you note that, please correct it. So, this is the orthonormal, the concept of orthonormal basis. So, now from the concept of orthonormal basis, I have E1 and E2, which are orthonormal to each other. Now, I try to find out this quantity, summation EI, I runs from, since this is a 2 dimension, n is 2. So, it will be 2. So, what value I will getting? E1, this will be my first term. If I expand this summation sign, and my second term will be E2, no cross term will be there, there is no ij. Please note that there is no ij. So, this term, now you know how to calculate this outer product. So, it is 1 0 this is 1 0 plus 0 1 0 1. So, my first term is 1 1 1 0 0 0 0 0. So, 1 0 0 0. My next thing is 0 0 0 0 0 0 0, this one, and this multiply 1. So, if I add, I am getting just 1 0 0 1, which is nothing but the unit matrix of order 2, because I am taking just 2 second order. So, I will get, if you do that for 3D, you will also get something 1 1 1 and so on. So, I can show that they are forming these things. So, let me write down the properties of the basis E have. So far we have 2 properties. One is EI, EJ is delta ij, which is called orthonormal property. I write ON. Second property that I have which is called completeness. which is called completeness. Apart from these two, another important property that also this basis holds. So let me write it. Say a matrix in 2D, a 2 by 2 matrix. I write this matrix in a component form where these are the components. Please note that if I write this matrix in this form, I can decompose this matrix in this way. Exactly like a vector, I can decompose my matrix in this way. This is the total decomposition of the matrix. So what I do that I will just multiply with some matrix which is this form. This is called the basis. Like the vector, this is also called the basis, but this basis is for the matrix decomposition. So this basis is coming from this matrix decomposition. So this is one basis, this is another basis, this is another basis. The most natural basis one can have. In 2D, by the way, E1 is 1 0 natural basis, E2 is 0 1 natural basis. I can write this expression, this quantity in terms of E1 and E2 also, just before I have just did it. So 1 1 will be how much? It will be E1 E1. 1 2 will be E1 E2. If I take the outer product of E1 and E2, please do that, then you will get this matrix. 2 1 is E2 E1, and finally 2 2 is E2 E2. So I can divide my entire matrix in terms of this kind of operator, which I define as a projection operator, but here this is a projection operator, but this is not a projection operator because 1 and 2 are here. This is not in the same direction. So now what I am trying to find out, that if this is given, how to find out the matrix element out of that. So matrix is given where these are forming a basis. So how do I get the matrix element? So this is my entire matrix A. So in order to find out AI, what I will do, I will first operate EI over A this side and EI over A in this side. Sandwich, I make a sandwich A with operating from this side and this side. In right hand side, what I will get, when I operate this from the left side, I will have a quantity like E1 E1. When I operate from the right hand side, I will have another quantity E1 E1. This is 1, this is 1, so I will have A1. What about the other terms? If you look that when I make a sandwich of this, it will give 1, but when I make a sandwich of E1 to E2, so let me write it, then it will be maybe clear. So A12 is simply E1 E1, it is okay, but then E2 E1, this is not okay, this is 0 because they are perpendicular to each other. So dot product or inner product between E1 and E2 is 0. In the similar way, I can also find 2 1, which is E2 E1 and then E1 E2 let me, so it is E1 E2 and then E1 E1 using this. Again I will find this is a 0 and finally the last value 2 2 which is both E2, so, and I am sandwiching then E1. So, I will get E1 E2 and E2 E1 E2 and E2 E1. This is also 0. So, this 0, this 0, this 0, this 0. So, A22, 21, 12 is not going to come into the picture, only thing that is there is A11. So, I will have my A11 component readily when I sandwich this. So, if I go with that, then I will find with the same treatment I can find A21, with the same treatment I can find A12, with the same treatment I can find A22 this. So, now another important property the E1 E2 E3 has, which is here if I write the third property, which is if I operate this EI over a matrix EJ, I will get back the matrix element Aij. This is called the matrix element. So, this is called matrix element. So, what in conclusion what I find, we find that E1, E2, E3, En are the n bases, in n number of bases by dimension n. It follows three important property, which is orthonormal property. Second thing is that they are complete, it is a completeness property, and third property that this is a matrix element. So, matrix element can be find out by these things. So, when these three properties are followed by this basis, we call it a natural basis obviously, because naturally it is coming, and it is very important to know that these three properties are followed, are coming from the concept of inner product only. So, inner product if you know correctly, then you can find out all these things, all the concepts are coming from inner product. With that today I would like to conclude here. In the next class we will go with more important thing, which is called the basis transformation, where we may require the concept of these few things. So, let us find out how in the next class how the basis transformation is working, how a vector is changing in another basis. If I a vector changing to another basis, how the vector formation can be put into that. That are the few topics that we would like to cover in the next class. With that, so thank you and see you in the next class.